Okay, so we're talking about molecular compounds, which are compounds whose simplest units are molecules. And a question arises is, why do stable molecules have the particular formulas they do? We know that molecules have distinct formulas. So for example, water is H2O, 2 atoms of hydrogen, 1 atom of oxygen. It never occurs as H3O or HO2. Those should look silly to you because they are silly. Well, the reason why is because of something very powerful called the octet rule. The octet rule is really the most important principle in chemical bonding. And it says that when atoms form stable chemical compounds, they do so by gaining, losing, or sharing electrons so that each atom has 8 electrons in its highest occupied principal energy level, or its valence shell, which you can also call it. So the question is, why? Why is 8 the magic number? Why is there something special about 8? Well, that should be pretty obvious to you by now, because 8 is the number of electrons that can fit into the valence shell. Atoms have 2 electrons in their highest occupied S sublevel, and can fit 6 electrons in their highest occupied P sublevel for a total of 8 electrons. So the driving force for formation of stable compounds is atoms achieving an octet, basically having a completely filled valence shell. So the question is, what can we do with that? Well, we can do something pretty powerful, which is we can draw Lewis or electron dot structures. A Lewis structure is a symbolic representation of a molecule, and it shows the following things. The nuclei and core electrons of each of the atoms in the molecule is represented by the element symbol. Shared electron pairs, that is covalent bonds, are shown as dashes or lines connecting atoms. And unshared, or also known as lone pair electrons, are shown as dot pairs next to the atom. Okay? And for examples, well, I can represent the hydrogen molecule, showing 2 H's to represent the nuclei, with a line or a dash connecting them. That line represents a bonding pair of electrons, a shared pair of valence electrons holding 2 hydrogen atoms together. I can represent the molecule hydrogen fluoride by showing a hydrogen atom bonded to a fluorine atom. However, in order for the fluorine to have its octet satisfied, I need to show 6 additional valence electrons around fluorine, and I show them as unshared or lone pairs. Fortunately, there is a pretty straightforward set of rules for drawing Lewis structures, and it goes something like this. You begin with the molecular formula, and you simply count the total number of valence electrons. How many valence electrons does each atom contribute to the overall molecule? Then you draw the skeleton structure of the molecule by connecting the atoms in the molecule with pairs of electrons that represent covalent bonds. If there's a carbon in the atom, it's always the central atom in the middle. If there is no carbon atom, put the least electronegative element in the center of the molecule. It turns out that nature tends to prefer symmetrical molecules. So for example, if the molecule has the formula AB3, meaning 1 atom of A and 3 atoms of B, then as you might guess, you'll put the A in the center and then attach the B atoms to it, giving you the most symmetrical structure that you can come up with. If there is any ambiguity whatsoever in how the atoms are connected, I will tell you what's connected to what, because sometimes it's not obvious. After forming the skeleton structure, you will have valence electrons left over. Give those away to the other atoms so that every atom has an octet of electrons. That is, so that by sharing electrons or by having unshared pairs of electrons, every atom is surrounded by 8 electrons. Finally, go back and check. Do you have the correct number of valence electrons shown? And do all atoms have an octet of electrons? Before we do some examples, let me point out some exceptions to the octet rule. First of all, obviously hydrogen does not follow the octet. If the fundamental principle is that atoms form stable molecules when they have completely filled valence shells, well, hydrogen cannot fit 8 electrons in its valence shell because its valence shell only consists of a 1s orbital. So hydrogen can only ever be surrounded by 2 electrons. What that means in practice is that the only thing you will ever see hydrogen do is form a single bond to another atom. Let's call it X. Okay? Because in sharing that pair of electrons with atom X, hydrogen now has 2 electrons in its valence shell, and it has basically filled its valence shell. Things you will never see is a hydrogen atom forming more than 1 bond, and you will never see a hydrogen atom with a bond and a lone pair on it. And those things are just so ridiculously silly, I will draw a big no through that. Don't ever do any of those things. Boron and beryllium. It turns out that these two elements, for reasons that are too complicated to go into now, can form compounds in which they have fewer than 8 electrons around the central atom. So for example, the compound boron trihydride exists, and boron in this case forms 3 single bonds to hydrogen atoms. It only has 6 electrons in its valence shell. Nonetheless, that molecule does exist. It turns out that there are molecules that have what are called expanded valence shells. We're not going to talk very much about these this year, but for example, phosphorus pentafluoride, PF5, actually exists in a form in which the phosphorus forms 5 bonds to fluorine atoms for a total of 10 electrons in its valence shell. We will look at molecules like this in our laboratory activity when we talk about molecular structure, but we're not going to cover these on test or quizzes. So let's go ahead and do some examples. The first example is iodine monobromide, IBR. Step number 1 is to count the total number of valence electrons. Well, iodine has 7 valence electrons, and so does bromine, for a total of 14 valence electrons. I will connect the 2 atoms with a pair of electrons to form the covalent bond. Of the 14 valence electrons I have to use, I have used up 2 of them so far. So I will just distribute the remaining 12 as lone pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. By doing so, I've used up all 14 of my valence electrons, and I have satisfied the octets of both iodine and bromine. Each of the 2 atoms shares a pair of electrons with the other atom. Each of the 2 atoms has 6 unshared electrons in its valence shell for a total of 8 electrons in its valence shell. And that is the Lewis structure for that molecule. Let's do another example. Sulfur difluoride. Sulfur has 6 valence electrons. Each of the 2 fluorines has 7. That gives me a total of 20 valence electrons. I will follow the rule of symmetry and put sulfur in the center and form 2 bonds to the fluorine atoms. Of my 20 valence electrons, I've used up 4 to form the 2 sulfur-fluorine bonds. That gives me 16 left, so I will give them away as lone pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And in this way, both the sulfur and the fluorines can have their octets satisfied. Sulfur shares 2 pairs of electrons with the 2 fluorine atoms and has 2 unshared pairs on it for a total of 8. Each of the 2 fluorine atoms shares 1 pair of electrons with the sulfur and has 3 unshared pairs, again for a total of 8. Nitrogen trichloride, NCl3. The nitrogen has 5 valence electrons. Each of the 3 chlorines has 7 valence electrons for a total of 26 electrons. I'll place my nitrogen in the center and form 3 bonds to the chlorine atoms, using up 2, 4, 6 valence electrons. 8, 10, 12, 14, 16, 18, 20, 22, 24, 25, 26. And in that way, both the nitrogen and the chlorine atoms have their octet satisfied. The last example is iodomethane, CH3I. Why don't you pause the video right now, get out a piece of paper and pencil, and try this Lewis structure on your own. Okay, let's take a look and see. Carbon has 4 valence electrons. Each of the 3 hydrogens has 1 valence electron, and the iodine has 7. That gives me a total of 14 valence electrons. I will place my carbon atom in the center, form 4 bonds, 3 to each of the hydrogen atoms, or I should say 1 to each of the hydrogen atoms for a total of 3, and 1 to the iodine atom. I've used up 2, 4, 6, 8 valence electrons. Carbon has its octet satisfied. Hydrogen, again following what's sometimes called the duet rule, is sharing a pair of electrons with the carbon, so it doesn't need any more electrons. So the remaining 6 valence electrons are going to go as lone pairs on the iodine, and then that way I can use up my 14 valence electrons. Okay, so there are 4 pretty straightforward examples of molecules and how you draw their Lewis structures. What about a molecule that has the formula C2H4? Well, this is going to be a little bit more complicated, but we can apply the same principle. Carbon, each of the 2 carbons has 4 valence electrons. Each of the 4 hydrogen atoms has 1 valence electron. 2 times 4 is 8 plus 4 is 12 electrons. Well, there is no single central atom, but I've got 2 carbon atoms, so it kind of makes sense that I should put them both in the middle and attach them with a pair of valence electrons for a carbon-carbon bond. I'm going to bet that the molecule is going to be as symmetrically as possible. So if there are 4 hydrogen atoms, I think probably the safest thing to do would be to put 2 on each carbon, like that. Of my 12 valence electrons, I have used up 2, 4, 6, 8, 10 so far. I've got 2 more to go. I can satisfy the octet of the carbon on the left by putting a lone pair there, but the carbon on the right doesn't have its octet satisfied. Okay. What about that? Still have the same problem. You might be tempted to split the difference and put 1 electron in each carbon atom, but that looks really weird. Well, it turns out in a situation like this, when you have given away all of your valence electrons, but haven't satisfied everyone's octet, you have to form a multiple bond. So that carbon atom, the 2 carbon atoms now are going to take that remaining pair of valence electrons and share it between them as a carbon-carbon double bond. And in fact, multiple bonds are not that uncommon in chemistry. So let's talk a little bit more about multiple bonds. Multiple bonds are formed when the molecule is electron deficient. As I said before, there are not enough valence electrons in the molecule to satisfy the octet of every atom using only single bonds and lone pairs. And multiple bonds represent 2 or 3 shared pairs of electrons. One important note is that halogens do not form multiple bonds. By the way, all of these little factual details, like the fact that halogens don't form multiple bonds and the exceptions to the octet rule, you do not need to memorize those. I will give them to you on tests and quizzes. So let's do a few examples of molecules with multiple bonds. CH2O is formaldehyde, 4 from carbon, 2 from each of the hydrogens, plus 6 from oxygen gives me 12 electrons. I will place the carbon atom in the center, and going with the most symmetrical structure I can come up with, I will form bonds to the 2 hydrogens and the oxygen. Of my 12 electrons, I've used up 2, 4, 6, 7, 8, 9, 10, 11, 12. Oxygen has its octet satisfied, but carbon does not. I don't have any more valence electrons to draw, so I'm going to erase one of the lone pairs of electrons on the oxygen. I'm going to move it over to form a second carbon-oxygen bond. Now that pair of electrons, instead of being localized on the oxygen, is being shared between the carbon and the oxygen. Okay? CO2 is carbon dioxide. 4 from carbon plus 6 from each of the 2 oxygens. 2 times 6 is 12 plus 4 is 16 electrons. I'll place the carbon in the center. 2, 4, 6, 8, 10, 12, 14, 16. Looks really bad. Carbon does not have an octet, so I will take a lone pair from one of the oxygen atoms, erase it, and move it over to form a carbon-oxygen double bond. That maintains the oxygen's octet and gets carbon a little closer. Now it's got 6 electrons instead of 4, but it still doesn't have an octet. So what do I have to do? Absolutely right. I have to do it one more time. Erase a pair of electrons from the oxygen on the right, move it over, and form a carbon-oxygen double bond. So in fact, carbon dioxide exists with 2 carbon-oxygen double bonds. Nitrogen, simple diatomic molecule. Each of the 2 nitrogen atoms brings in 5 valence electrons for a total of 10. Nothing else to do but bond them together. 2 electrons used up. 4, 6, 8, 10. Well, if I erase a pair of electrons from one of the nitrogens and move it over to form a nitrogen-nitrogen double bond, that helps. The nitrogen atom on the right has its octet satisfied, but the one on the left doesn't. So what do I have to do? Absolutely correct. Do it one more time. And in fact, the dinitrogen molecule, the stuff that you are breathing right now, has a nitrogen-nitrogen triple bond. The last example, C2H2, is acetylene. Why don't you pause the video, pick up your pencil, and see if you can solve the Lewis structure of that. All right, each of the 2 carbons has 4 Valence electrons, each of the 2 hydrogens has 1. 2 times 4 is 8, plus 2 is 10 electrons. I'm going to guess again that the molecule is as symmetrical as possible, so I'm going to put the 2 carbon atoms in the center, bonded by a pair of electrons. The most symmetrical way to arrange things would be to place 1 hydrogen on each carbon, which is what happens. 2, 4, 6, 8, 10. Looks kind of like the problem we just had before. So if I erase one of the pairs of electrons, now the carbon on the right has its octet satisfied, but the one on the left doesn't. So again, I'll have to erase a pair of electrons, move it over, and in fact, acetylene has a carbon-carbon triple bond. So one question that arises is, how would you predict that the lengths and energies of multiple bonds would compare to those of single bonds? Well, keep in mind what's holding a covalent bond together. If I represent a carbon-carbon single bond by this little picture where I've got positive charges to represent the nuclei and negative charges to represent the electrons, remember that the ultimate source of the bond is the mutual electrostatic attraction between the positively charged nuclei and the negatively charged electrons. If I share more than 1 pair of electrons, then I'm increasing the number of oppositely charged particles and I'm increasing the overall electrostatic attraction. So for example, if I were to share 2 pairs of electrons, now each of the positively charged nuclei can feel the attraction of not 2, but 4 negatively charged particles. And you get the basic idea. So the general idea is that the more electrons that are shared between 2 nuclei, the overall greater electrostatic attraction there is among oppositely charged particles. Therefore, the closer together the nuclei will be, and the stronger the bond will be. Let's look at some actual numbers. Carbon-carbon single bond has a bond length of about 154 picometers and a bond energy of 346 kilojoules per mole. Carbon-carbon double bond, sharing now 2 pairs of electrons instead of just 1, the bond length decreases to 134 picometers and the bond energy increases to 602. Carbon-carbon triple bond, even shorter bond length, 120 picometers, and a bond energy of 835 kilojoules per mole. Okay.